This video will cover the theory of resonance. The theory of resonance is based on the fact that many molecules or ions are best described by more than one Lewis structure. In other words, we say that the real molecule or ion is a combination of what are called contributing structures. And these contributing structures are all of the Lewis structures that together can describe the molecule or ion. And what we say is this molecule or ion is called a resonance hybrid. It is a hybrid structure made up of all of the different contributing structures for that particular resonance hybrid. This theory is best understood by looking at examples, so we'll start with the example of the carbonate ion, which is CO3 2-. And the carbonate ion is made up of 3 contributing structures. The Lewis structure for the carbonate ion looks like this. So it's a carbon attached to 3 oxygens. One of the oxygens is connected to the carbon with a double bond, the other 2 with single bonds. They have 3 lone pairs each and therefore a formal charge of -1. The Lewis structure I've just drawn, however, is only one of 3 contributing structures to the resonance hybrid of the carbonate ion. So I'll draw the additional contributing structures. Another contributing structure looks like this, where we've moved the double bond and the charges onto different oxygen atoms. And then finally we can draw the last contributing structure, where the double bond is on this oxygen. So these are the 3 contributing structures to the resonance hybrid of the carbonate ion. Now, to indicate that these are all contributing structures to the same resonance hybrid, we connect them with these double-headed arrows that I've drawn. We also enclose the contributing structures in brackets. So this is the complete structure of the carbonate ion. I just want to bring your attention to the fact that resonance arrows are different than equilibrium arrows. They look different and they mean very different things. So it's important to remember to use the correct one when you're talking about resonance, which is this double-headed arrow. So what we say is that the actual structure of the carbonate ion is a resonance hybrid of these 3 contributing structures. I'm going to actually draw what that looks like in a moment. And you might be wondering why it matters which oxygen has the double bond and which have the charges. And it actually is important when we look at what the overall structure with the combination of these contributing structures with the resonance hybrid looks like. So let's draw that now. What the actual structure looks like is a combination of the 3 structures, the 3 contributing structures that we've already drawn. And so what that means is there's some double bond character on each of these bonds between carbon and oxygen. And so we'll indicate that with a dotted line. So those extra electrons of that double bond are spread out over all 3 bonds. And that also means that the negative charges are spread out over all 3 oxygen atoms. And so we give them what's called a partial negative charge in the actual structure. This little delta means partial. So it has, each of those oxygens has a partial negative charge. And of course the overall structure has a charge of -2. Another way to say this is that the charge is delocalized across the 3 oxygens. And this is important because resonance is often something that stabilizes a molecular ion, and it does so by delocalizing charge, by spreading the charge out over multiple atoms so that it's happier, that it's more stable. When you're trying to draw resonance structures or contributing structures to a resonance hybrid, there are some rules in order to draw valid contributing structures to a resonance hybrid. So the first of those rules is that all of the contributing structures that you draw must have the same number of valence electrons. If the number of valence electrons changes, you're not drawing contributing structures, you're drawing different molecules or ions. The second rule states that all of the contributing structures must not violate the octet rule. And so what that means is for atoms in the first row, they cannot have more than 2 electrons. For atoms in the second row, they can have no more than 8 electrons. And for atoms in the third row, they can have no more than 12 electrons. And those maximum numbers of electrons have to do with which shells are available for holding valence electrons in each type of atom. And then the final rule states that the positions of the nuclei must remain the same. Only electrons can move. If nuclei move, again we're talking about a different molecular ion rather than contributing structures to the same molecular ion. Now let's look at an example. We are going to draw resonance structures for the following molecule. Okay. There is one valid contributing structure to the resonance hybrid of this molecule. And that contributing structure looks like this. So this is a valid contributing structure to the resonance hybrid of this molecule. What I've done is I've moved electrons. I've moved electrons from this nitrogen into a double bond with a carbon, and I've taken electrons from this double bond and moved them onto the oxygen. And so what this does is it creates a resonance contributing structure to the resonance hybrid that follows all of the rules we've talked about previously. And to illustrate these rules, I want to show you some incorrect contributing structures to this molecule. So the first incorrect contributing structure that we'll look at is this one. And this contributing structure, or this structure, is not a contributing structure to the resonance hybrid because it breaks the third rule, because one of the nuclei has moved. This hydrogen was on the nitrogen and is now on the oxygen. So this is not a contributing structure to the resonance hybrid shown above. Another structure that is not a contributing structure to the structure we've drawn above is this one. This one breaks, again, the third rule in that not only has it moved a nucleus, but it's completely removed a nucleus. Right, there were 3 hydrogens on this carbon, and now there are only 2. This is a different ion than the structure drawn above, because it's a different number of nuclei. Additionally, it has a different charge. You'll notice that in the contributing structures I've drawn above, the overall formal charge for both of them sums to 0. In the structure I've just drawn, it sums to -1. That's another way to tell that this is not the same structure, because the overall charges should add up to be the same in every contributing structure you draw to the same resonance hybrid. So this is also not a valid contributing structure. Let's look at another structure. This structure is also not a valid contributing structure to the original structure that I drew. And the reason is it violates the first rule. it has extra valence electrons. The other way that we can tell it has extra valence electrons is that its overall charge is -2, which indicates that we've gained electrons. So this is not a valid contributing structure. What about this structure? This structure has the same charge as the original structure, but it's not a valid contributing structure, again because a nucleus has moved. There were 3 hydrogens here, now there are only 2, and the extra hydrogen is attached to the oxygen. If a nucleus moves, it's a different molecule, therefore this is not a valid contributing structure. Finally, let's consider this structure. This structure is not a valid contributing structure because it violates the octet rule. This carbon has more than 8 electrons in its valence shell. That's not possible. Therefore, this is not a valid contributing structure. So hopefully that helps you understand a little bit about how to draw proper contributing structures to a resonance hybrid.